Welcome, everyone. As Michelle said, I'm Brian. I'm the co-founder and CTO at Voxel, and very happy to be here today to tell you a little bit about what is new in the latest release of 51. First, an important disclaimer already alluded to. Everything that you're about to see is free and open source. So if you like what you see, we would love your visit at the project's GitHub repository. Give us a star if you're so inclined. No pressure, but always appreciated. Quick aside, if you're new to 51, I'll just give you a quick elevator pitch about the purpose of the tool and the problem that we're helping you solve. So the setup is pretty simple. In the machine learning world, there's data and there's models. In the past, maybe most of your time was spent on models, a lot of innovation with model architectures, really cool stuff, not slowing down in any way. However, studies have shown that the typical data scientists in their real job or executing on a project, whether it's a hobby, research, or production quality, a vast majority of the time, and even increasingly so in the future, is actually spent on data wrangling and not on the models themselves. And so the key challenge that data scientists have is how can they make that data-centric work more efficient, and how can they increase the quality of their data sets? Why does data quality matter? Well, if you're developing a self-driving car and you feed it bad data, it might crash. If you're developing a consumer product like Google Photos and you're trying to do some machine learning, but the data is not representative or unbiased, your system may have biased results and may lead to big issues. We can even put a number on that. We've done some research on the dataset Open Images from Google that showed that actually 30% of so-called false predictions from a state-of-the-art model on that dataset are actually not due to the model at all, but rather the data that it was trained on. And so again, data quality is really important. Our company exists to help increase the transparency and clarity of the world's datasets. That means your datasets too. And we do that by providing data-centric tools to help you address data quality issues. 51 is the open source project that makes it all happen. It's what we're going to be looking at today, including all the new features in it. It's there to help you organize, visualize, search, and explore your visual data sets. That means images, that means videos, point clouds, more modalities coming soon. Workflows like integrating with annotation, finding and fixing labeling mistakes, analyzing your models, finding their weaknesses, running workflows to help identify those issues, and we'll see some cool tools to make that happen in a second. Think of 51 as glue between your data sets and your models, and also between your data-centric tools and your model-centric tools. So if you have an annotation vendor on the left, and then you have a ML model training framework, experiment tracking tool, and so on the right, 51 kind of is the glue that holds those things together and helps you build workflows to make sure that you're curating high quality data sets on the left and making sure that you can feed them to your models and close that loop and iterate on those data sets. Like I mentioned, 51 supports all types of visual data, all different types of tasks. We'll look at a few different tasks today, also geolocation, a lot of cool features coming with embeddings, which we're going to be paying particular attention to in this talk. All of those things available through a Python SDK to load in data. And then here you're seeing the application that you can launch with the open source tool as just a local web server. It lets you visualize all that data, organize panels of information. You can think of the app as kind of like a VS Code for your data sets. So with it, you can organize the data, open up different panels of information to explore your data sets in different ways. It also has a really powerful Python SDK. I'll be pulling up a Jupyter notebook in a second to do a demo, and you'll see a taste of that. But everything that you can do through point and click in the application, you can do that and even more through the Python SDK. You can think of it like a pandas for your computer vision data. So more information available at 51.ai for that documentation. There's also the Brain. This is a component of the tool that provides some canned workflows for specific things I mentioned earlier, methods to help find model failure modes, methods to integrate with annotation providers, and then tools like embeddings and things like that to help you automate workflows like finding annotation mistakes and so forth. We'll see some of those in a second. Just wanted to make sure you're aware of that. That's called the Brain. Just a fun fact, we recently crossed 1 million downloads with the open source project. Super excited about that. Thank you all if you've downloaded the tool. If not, maybe you'll do it for the first time today and add a few more downloads. So let's get right to what's new in the latest release. That's 0.20. This release was focused a lot on embedding workflows and different ways to search your data sets. So if you have annotations, you can, of course, search by specific content that you're already aware of. Like you can find cats in your data set if you have ground truth annotations for them. But what if you don't have annotations yet? Well, there's still a lot of interesting things you can do. And in this release, we sort of leveled up the support for a couple different search workflows. The first thing I'll show you is that you can search your data sets by natural language now in a completely unsupervised way. You can have any data set, you can just load in a bunch of images. And then once you add what we're calling a similarity index to that data set, you can then directly search that data set by natural language queries, any type of query you want on any data, and find nearest neighbor results to that query. Pretty cool stuff. It's enabled by integrations that we've added with vector databases. So we integrated with Qdrant and Pinecone, a couple leading open source and commercial vector database solutions, respectively. So we'll dive into how you can configure those and also how you can use the default index that we provide in the project. And then finally, we'll close off with some demos on new features related to point cloud datasets. So without any further ado, let me just jump right into a Jupyter notebook so we can see the natural language search feature. So this notebook on the right, this is a common way that users will work with FiftyOne. It's a Python library, of course. You can install it through pip if you haven't already. Pip install FiftyOne. From there, here's an example of loading a data set. So I've imported the library. I loaded a data set from our zoo that's sort of built in. And then the first thing I want to do is show how to use the similarity search feature. So to do that, we'll use a method from the brain called compute similarity. What that's going to do is load a model from the zoo. We'll talk about that in a second. This is a model that can generate embeddings for both language and images. So what's happening here is the model is loaded. It's generating embeddings for each image in the data set. This particular data set has 200 images, so the embeddings are computing here. That's actually just running on my machine here. And then I've given it a name. In the FiftyOne project, it's called a brain key. And this is an identifier that's used by the rest of the system to refer to this index that was computed. I will not dwell right this second on what that index is. We'll talk about it in a second. But basically, now that I have this data set and I have this index on it, I can go ahead and launch the app. I already have it actually open in another window here. So I'll just refresh. And the point is that if we focus now on the app, the new feature in this release is this magnifying glass icon here. And this is letting you search your data set by natural language. So this data set happens to have annotations, but the point is that those aren't necessary. So I'll just turn those off to avoid confusion. It's a data set of 200 images. And what I can now do is basically type anything I want into this search box. What is happening now? It's the first time you do a search, it has to load that same model. So it takes a bit longer the first time. It then generates an embedding for that search puppies, and then returns by default the 25 most closely matching images in the data set. And again, this search could be anything. So for context, I could try something a little bit more complicated. So maybe I could search for kites high in the air. And here we go. This data set may have annotations for those things, but again, this search feature is completely unsupervised. It's not relying on the annotations, only based on the embeddings that we added to the data set. Just to scale this up a little bit, let me jump to a larger data set. That data set had 200 samples. So here's a subset of the COCO data set, the validation split. Here we've got 5,000 samples. So a little bit more content here that I can search against. I can run, let's see, food on plate. Let's see what happens here. Pretty good results. So in this search UI that we're seeing here, I'm just kind of using the most simple syntax where you just type and go. If you're curious, first of all, you can click on the info icon to get more documentation about using this feature. It'll take you to a page in the documentation here. We'll go back to the code and sort of show some more examples. So I won't dwell on this for now. You can also click on the gear icon to see some advanced settings. So here you can see this is the reason why it returned 25 best matches. That was the default. You can change that here. If you have multiple indexes on the data set, you can choose which one you'd like to use. So just a little bit of information there at your fingertips. So before we talk more about using this feature, I want to just go back to explain a little bit about how vector search works, in case you're not familiar. So we did natural language search. It seems pretty magic. How does that actually work? Well, like I mentioned, the technology that's being used there is vector search. And so the basic idea is that you may have some type of data. Maybe it's images, maybe it's a document, maybe it's text or audio even. Suppose we have a way to transform that data into what's called an embedding. That's a vector representation of that content. Let's pick a typical number, a vector of length 1024. Then let's suppose that we do this for all of the content in our data set, right? So on the left would be the data set, 200 images in the case of the first example I ran. And then on the right, suppose we have some kind of query. In the simplest case, the query would be the same type of content as the data set. But actually what I just showed was a multimodal situation where the data set was images, but the query was text. So there's models that support that kind of workflow. We'll see in detail the one that was used. But suppose we could generate a corresponding vector of the same length that represents that query. Well, then we basically have a problem of searching amongst a corpus of vectors for the nearest neighbors of the query vector representation. This is a known problem. In principle, for very large data sets, finding an exact solution can be quite complex, but there are solutions built, these are called vector databases, that are designed to optimize these kind of queries using graph structures and other sort of CS 101 and beyond concepts to make that search fast. So that's what we mean by a vector database. And this query is exactly what was happening behind the scenes when I was using that feature. So what model was being used? Well, this is a model called CLIP from OpenAI from, I believe, last 2 years ago. So CLIP stands for Contrastive Language Image Pre-training. What does that mean? Well, it's basically depicted on the left here. So these are models that are trained on pairs of images and text. So during training, the model was fed an image and then a corresponding text string that relates to that image. Imagine a caption. So in this example here, it's a picture of a dog, and then the text is Pepper the Aussie pup. The model's architecture has two encoders, an image encoder that's designed to translate the image into a vector, and then a text encoder that's designed to transfer the text into another embedding vector. And the model is basically trained to learn encoding representations such that the text and the corresponding image are as close together as possible. So if you imagine from a probabilistic standpoint, the statistical properties of these encoders should be that the entries of the vector pairs should be very highly correlated. So the correlation matrix should be close to identity. So this model has been fed millions of these pairs, and suppose that training is possible, and thank goodness it is, because what you get out of that is a pretty cool system. Basically, what we have now is a pair of encoders, and you can basically use the image encoder. You can feed it at inference time a bunch of images of any kind. It'll generate a bunch of vectors that represent its understanding of the content. And then at inference time, we can feed either an image or a text to the model, get the corresponding embedding, and then run a vector search against the database to find the closest matches. And the cool thing is that in the case of language search, that would enable you to do a text search and return matches that are images. But if you can see, there's nothing special about searching against an image data set for text. You can either do it, you can do it in either direction. You could either take an image and produce some proposed captions, or you can take a bunch of images and search by text and find the closest images. And so what that means is that this feature that I was demoing here in the app, it doesn't only work with text queries. You can also search image to image. So if I select an image here, now there's not a magnifying glass icon. Now there's an image similarity icon. And I can simply say, okay, show me the similar images in my data set to the one that was selected. It's using the same model. It's using the same similarity index that I added to my data set. Nothing else was done behind the scenes. Basically, when you generate one of these indexes, you can now search by images, or if you used a model like Clip, then you can also search by text in the app. And so the way that works in the tool basically is that if you have an index on the data set that supports text prompts, then you'll be able to use this magnifying glass icon. And if you generated embeddings that don't support text queries, then basically you'll see a link to the documentation here, but you won't be able to use that feature. However, you still can select an image and do a search like that. So it'll always be allowed. So hopping back into the presentation. So far, all the code that I ran, it's totally valid. You can run it. However, those vector searches are being done using a built-in vector database, something that just runs in memory. But if you want to scale this workflow to very large data sets, let's say millions of images, and you want to be able to quickly do searches across those millions of data points, then it would be more performant to consider using a dedicated vector database solution. So as of the 0.20 release of FiftyOne, we integrated with two vector databases, Qdrant and Pinecone. And so in the example code that I shared before, I was basically running the compute similarity method. And the upshot is that the method now supports a backend parameter that you can either set to the default to use the built-in database, or you can specify one of the two supported backends. And assuming you've configured your vector database account or keys, we'll look at examples of what that means, then you can generate indices for your FiftyOne data sets where the vectors are stored in that separate database. And then when you do a search in the app, it'll be querying that database rather than doing anything local. So let's see what that looks like. Back over in the code, let me skip over patch similarity for 1 second. We'll come back to that. So here I've skipped to the Qdrant section. Qdrant is an open source vector database. So actually getting set up with that is as simple as pulling their Docker image of their server and running it, and then installing their Python client. I've already done that. And by the way, there's a link to the documentation here that you can find on our website that sort of covers all the details of how to set it up. So what I basically did was follow the instructions in the setup section here. And then the point is that I can now create an index specifying the backend parameter to Qdrant. And now this will be a similarity index on my data set that uses Qdrant rather than the default. And then just to show some more flexibility that is coming with this current release, in this syntax here, I'll run it first. So what has been done here is that the index, I created a Qdrant index. If I list here the brain runs, I can see that I have the original index that I created, and now I have one for Qdrant. However, I didn't add any embeddings to it yet. When I specified embeddings equals false, what I was saying is that let me just create the index, but not add the embeddings yet. And then in this .20 release, there was a bunch of methods added to the similarity interface to make it easy to update indices that you've created. So in this particular example, I already computed embeddings for my image index, and the embeddings that's a separate concept. Those embeddings just came from Clip. And so this is just for illustrative purposes, showing that you can run a simple command to retrieve the embeddings from an existing index. So let me do that here. So now this embeddings is a just like a NumPy array of 200 512 dimensional vectors, and then the corresponding sample IDs of the samples in the 51 dataset. So now I created a Qdrant index. It has no embeddings in it yet. So let me just add those pre-computed embeddings to the Qdrant index. And then I can check that its size is 200, like I expect. And now if I refresh, we'll see that I have a second index on the quick start data set that I was working with. Now, if I want to do a search, I have the previous index, or I could switch to Qdrant instead. And now I can do searches against my Qdrant index rather than the built-in. Pinecone is also supported. So again, integration documentation is available on our website. Pinecone is a commercial vector database solution. So in order to use it, you'll need to create an account and then download an API key and then install the Python client. And from there, the same workflow is possible. When you create a Pinecone index, I can do it here. I'll create an empty one. It will work. And then I can see that I gave it another key, so it's available in my data set. And for the record, you know, these vector indexes, they are saved on the data set. And so if I mark my data set as persistent, let me insert a cell. Now I've marked my data set as persistent. That means if I were to close my 51 session and open it up later, that data set would still exist. I could load it like this. And these similarity indexes, the metadata associated with them are stored on the 51 data set. So at a later date, I could simply load the index back, and then I can continue on and do the workflow that I'm about to do now. Now I'm doing it within the current session, but it can always be done across multiple sessions. If you're curious, you can see the information about an existing index. You can do dataset, get brain info. I can see the information about when I created this index and what parameters I provided it and so forth. So for example, when you work with an external vector database solution, there's an external collection in Qdrant terminology or an index in Pinecone terminology. So here's the name of that index. if it's of interest to you, you could customize that index by providing a custom name here. You can also see there's a number of other parameters that you can configure programmatically if you want. Incidentally, if you create an index offline, you could simply pass the name here to connect to an existing index. That's also allowed. In any case, I've created this index. Let's suppose that this is the first index I've created on this data set, so I don't have any embeddings yet. Notice that when I created the index, I specified the name of the model that I wanted to use. That information is stored on the configuration for that index. And so actually, if I just want to add some embeddings to that index for a particular data set, I can do that with just one line of code. So here, I'll go ahead and run it and explain while it's running. So I'm taking an empty index and asking it to compute embeddings for a data set that I passed to it. And so it has loaded this model and is computing the embeddings. So when that finishes, then we'll simply add those embeddings to the index. And by the way, there's documentation about this, this interface available on the docs. I can show you where that is. We're talking about user guide, brain, similarity. So I've been working with the Similarity API. So here it's explaining how you can configure it. And then what we've basically been running through now is how you can create an empty index, and then different techniques for adding samples to an index. It's also possible to retrieve embeddings from an existing index. We already showed that. It's also possible to remove embeddings from an index, and then of course, delete the index if you no longer need it. Let's see what happened here. So failed to connect to Pinecone. That happens sometimes. Let's try this again. By the way, the embeddings were already computed. I didn't have to recompute those. All right, so that time it worked. Now we have a Pinecone index that also has 200 samples in it. So if we go back to the app, refresh. Now I can choose the Pinecone index to search against. Same workflow, just the ability to choose between indices. Now, not only can you search against images, you can also search against object patches. So in FiftyOne, if you have a data set with bounding boxes or polylines, then you may know that you can switch to a patches view of that data set, where you're now looking at one sample per object patch. So it's also possible to do direct similarity searches or text searches against those patches. In order to do that, you will have to generate a new index. So that is described here in my notebook. So I'll just start it and then explain. What I'm doing is saying, I want a new similarity index on my data set. I want to use the same clip model from before, but I want to embed not the images, but the patches of the images that are defined by the bounding boxes in the ground truth field. So here, I can see that I'm working with the ground truth field. So in this case, it's working over the data set, but it's embedding not the images, but those patches. And so you can see here that there's 1,232 patches in the data set. So once this index is generated, when I look at its length, it'll be 1232 instead of 200. And we'll see how you can do a search against that. Also should mention, where is this magic string coming from? So the model argument of compute similarity Let's see if I can. Can't see the method signature until the function's done. So that string is coming from 51's model zoo. So 51 contains, if I go here, a bunch of models that are sort of natively available. So when you run them, their pre-trained checkpoints will be downloaded to your machine. So we're using a clip model, which is one of the models in the 51 zoo that supports multimodal embeddings. And so this is basically showing how if you wanted to directly load that zoo model and apply it to your data set, you can do so directly. But in this case, the argument to the function that we're working with understands the names of zoo models. And so I'm providing the name rather than the actual model instance. But in any case, that index has been generated. Here's the signature of that function that popped up finally. So now I have another index on my data set. I called it, oh, that's image here. It's called GTSim for ground truth similarity. Obviously, the string is mine to choose. So now let's see how you'd use that. So in the app here, I switched to a patches view. And so I probably should refresh first. Now, the search icon is still available, but if I were to do a search for fork, it'll search against the patches, not the entire image. So it's not taking into account the rest of the image, just the embeddings for the patches. And as per usual, I don't have to use the search, the text search. I could also do an image search. So if I'm curious to find things that look like this cake here, I can select it. And now I have the image search feature instead. So I can find things that look similar to that. All of this works if you use a Qdrant or Pinecone index as well. It's all the same operation. It's just a matter of whether the index exists. Now, I can also do these searches not through the UI, but through code programmatically. So here's an example of what it would look like to do a search against a patch index. So the first thing I want to do is transform my data set into a patches view. So if I run this command by itself, this is a view that contains one sample per object patch in my data set. And once I've done that, basically what's happening when you do a search here, I'll do another one just to illustrate. If I do a search and then I click the bookmark to see actually what was happening, what 51 was doing was creating a view stage called sort by similarity. And so I could always just do that manually myself through code. So here is an example of that. Here I did a search where I took my patches view and then I added a sort by similarity stage and specified the name of the index to use. And so now I've created programmatically those 15 cute puppies. And remember that 51 is interactive in open source mode. And so on the left, I have my session and I created a view. So if I want to, I can just set the session view property and programmatically update. So now I'm looking at that particular view that I created with cute puppies. You can also do this with image similarity searches. And rather than providing a query text, this query could also be an ID of a sample. So just to illustrate that. Let's see. I will, let's select this image. So here's the ID of the selected image. Then let's generate another view where I sort by similarity to that sample ID instead. You can actually also provide a list of sample IDs. If you want to select multiple images, you can do a search, like a composite search, similar to both of those. So I can provide a list here, that's fine. So in this case, I selected an image. So what I need to do is specify the name of an image index on my data set. So the image ones I have to choose from are the first one I created or the Qdrant or Pinecone ones. So I'll choose the image one. So what happened here is it did a search, basically the same search as if I have the same thing selected here. And so if I were to just click show similar samples, it would programmatically do that search. But I've already done it through code. So if I update, I'll see the same results of that query. Cool. So we've covered Qdrant and Pinecone. We talked a bit about the Similarity API. Again, documentation is available at FiftyOne.ai. I kind of went through what's shown here. In 51.20, the similarity indices are now mutable. So you can add new embeddings to an index, retrieve embeddings from an index, or remove them. So finally, let's wrap up by looking at some upgrades to point cloud support in 51.20. So in previous versions, you were able to work with point cloud data. Let me show that real quick. So here's a data set that's available in the zoo, a grouped data set. So this grouped data set contains both images and point clouds. So if I load it here in the app, what I'm seeing here is a data set that has images, but also has point cloud data. So here, if I click into a sample, I can open up a representation of that grouped information where I can look between the different images that exist in this sample, as well as the point cloud visualizer. That will show me the point cloud data I have. A number of different controls exist for point cloud data, by the way. You can toggle the grid on and off. You can change the size of the points. You can choose how the point clouds are shaded, either by Z value or intensity, the radar distance from the scanner. You can also provide RGB values for your point clouds. So a lot of controls exist there to configure that. However, what was not previously possible was actually seeing this, being able to work with point cloud data sets in the grid, or even a standalone data set. Previously, you had to use group data sets. And so what is now possible, I can take this grouped data set and I can run a utility that exists in the tool to generate projection images. So what it's doing is taking each of the point clouds in the data set, and it's generating what we're calling an orthographic projection image, like a top-down projection of that point cloud, and then storing those in a new field of the data set. And the reason that's useful is it gives you a way to explore those data sets from the grid view here. So now when I open up the grid view, I have sort of like a fast rendering representation of each of those point clouds. So I can kind of quickly scan through to find the one of interest. And then if I want to click into it and work with it in 3 dimensions, I can then open the modal and work with the full 3D scene here. Again, the method that I ran there, it's called compute orthographic projection images. And if you search in the docs for point cloud datasets, you'll find more about that. So here under, I'm in the user guide here, and I'm looking at point cloud datasets. This page here kind of shows all the different modalities that you can work with, point cloud being one of them. And it's explaining how you can create a sample for a point cloud dataset, add it to a dataset, and some information about how point cloud data itself is structured. Also some information here about how to create 3D labels for those scenes. So, in this scene that I was looking at here, I have some object detections. Oops. So these 3D objects here, obviously those are stored as labels in a field of this data set called ground truth. And so in the documentation, you'll find documentation for how to create those objects. So when you're working in 3D, you have a detection object, and then you specify its center and its dimensions and its rotation about its center. And so with that information, you can describe a 3D box, a cuboid in 3D space. You can also create polylines, lane markings, arbitrary shapes, and so on. Those are also possible. So that's point cloud support in 51. And then again, the change that was made here is there's now a utility available to help you automatically compute those projections. And then just to illustrate the point, it's therefore now possible to work with a data set that only contains point clouds. So just as a quick way to make that happen, what I'm doing here is taking a grouped data set, the one that we're seeing on the left, extracting only the PCD slice of it, and then cloning it into a new data set. So now here I have a PCD data set. I've printed it so you can see that it's a data set whose media type is point cloud. It has just those 200 point cloud samples. And then that method I ran here to generate those projections has placed a new field on the data set that contains those orthographic projections. You can print so you can see. Why don't I? So it stores the path to the projection image on disk, its dimensions, and its bounds in 3D space, so that when I view this data set in the app, here I'm looking at basically the same data set, but now it's only the point clouds. So there's no selector here. This is the temporary data set I created, and it has only the point cloud data. And then when I click in, I see just the 3D visualizer. All right. So that's basically what I wanted to cover about point cloud datasets. I did already kind of flash some of these things while I was demoing, but just wanted to highlight that there are some new controls that came in this release. When working with point cloud data, you can adjust the sizes, turn on and off the grid floor. You can configure the viewer to show and hide different sections of it for 3D data sets. And actually, in all the cases of features I've demoed today, the app has gotten a bit smarter. So if you have configured a setting, it should remember that setting for you in the future. If you have multiple similarity indices on a data set and you configure it, It should remember that, and any future searches will use the same index unless you change it again. So just a few more niceties to make your life easier. Wanted to give a quick shout out to a few folks from the community that contributed to this release. This release window was only a couple weeks, so there was 3 contributions that made it in. Thank you so much for doing that. Really appreciate it. If you yourself are interested in getting started with the project, we would love to have you. A good way to do that would be to go to GitHub issues and search for issues that are marked as good first issue. If you are interested in picking up one of those, feel free to leave a comment, and we'd be happy to help make sure that you can get started.